Good morning, everyone. Welcome to the morning session. I'll be the chair, Mattia Rezal. So we have three talks this morning with a half an hour break after the first one. And I'm actually quite looking forward to an interesting discussion based on the title of the talk. So Karem Sakallah will give us a roadmap for the next phase of SAT research, please. Karem.
All right, thank you very much. Good morning, everyone. And this is going to be somewhat different. It's not going to be a very technical talk, maybe a policy talk of sorts. I give you a pragmatic problem-solving approach to research, right? It's different from other ways of doing research. And I've heard several conjectures yesterday from various speakers. I want to make a conjecture over here. And the conjecture is, if a human created it, designed it, then we ought to be able to analyze it. Okay, just keep that in mind as we go through this. And just to see how many friendly faces are in the audience, I want to just ask, how many of you use yourselves as proof theoretic types here? Proof theoretic, people who do theory. Proof theory, okay? Okay. How many of you are kind of geeks who just code and do program, write solvers? Okay. Okay. And what about the rest of you? You're neither of these two groups. Why are you here? Okay. Okay. So I think some of what I'm going to say, I've said it before, but it didn't kind of make much impact. And some of what I'm going to say may sound harsh, but it's not meant to be, kind of offensive to anybody in person. It's just that I'm really concerned about where we are with this, field, right? And so it's meant to start a conversation about how we can bring the theory people and the empirical people together to actually work together. We've been meeting like this for a number of years, maybe 10 years or so. And every time the theory people talk to themselves, the implementers talk to themselves, and there is no communication between the two. So I might not have the right answer here, which is fine. You can, corner me in the break and tell me that, I'm, full of it. But I think I have an idea of how we can make this work. Okay. Now, this is a success story in a very unlikely collaboration with Armin Beery, who has written, I don't know how many solvers he has written so far. Anybody has a count of how many solvers he has written? Dozens, right? Okay. And me, who has who have not written any solvers. Okay, I didn't write any solvers. So I'm neither a coder nor a theorist. I don't know what I am. It's just a random crank, right? So I want to acknowledge both Armin and his postdoc, Matthias Flery, who should be on Zoom. And when there is a chance for them to kind of speak up, we let them talk. And I'm also going to acknowledge Jaiwei Chen and Jonathan Feseha, who are not my students. They took my class on formal verification and became very interested in SAT, and they're volunteering to kind of help with what I'm going to show you. Okay, so here is kind of what we're going to talk about. I'm going to give you a little brief history of CDCL. That's my own brief history because I know some things that happened that probably nobody else knows. Then I'm going to talk about the phase transition hoopla. If you don't know what that is, I'll mention that in a few minutes. And then I'm going to give an attempt to explain the performance of CDCL. Then talk about the SAT competition. There's Mariah. Oh, yeah, I'm going to talk about the SAT competition. And then I'm going to talk about, okay, skip this one, a prototype that Armin developed called tabulator SAT, and then give you just a sense of what we can do that we're not doing right now. Okay. So the unintended birth of GRASP. How many of you how GRASP came about? You came a little bit late, early adopter, but how did it actually happen, right? This is how it happened. I'm an electrical engineer, okay? I solve problems. I don't do theory. I like math, but I like the math that helps me solve problems. So we had a big project to do timing analysis, okay? we had chips that we needed to know, does it run at 500 megahertz? Back then it was kind of a big deal, 500 megahertz. And so you get a circuit like this, and you say, okay, assume unit delay on all of the gates. I wiggle this input here. How long does it take to reach the output Z? Okay, it's a traditional problem in critical path methods. You can just say if each one of those gets a delay block. And what is the longest path here? 7. Okay, so I can go like this, and I can say 1 to 0 here goes 1 to 0 over there. That was what we were doing. Turns out that is an infeasible path. Why is it infeasible? Well, because when we ignored the logic, it was feasible. But if we allow the logic to be taken into account, meaning if I have to go from X1 to A, X2 must be 0. Otherwise, it will block it, right? There's an OR gate here. If we want to go from A to B, I have to have X3 equals 1. Otherwise, it will block it here because a 0 on this input would block the transition. And so on and so forth. You can go through this, right? And you get to this gate. Now, to go from D to E, I got to have X3 being 0. Otherwise, this OR gate would block it. But X3 is already 1. So we have an inconsistency. There is an inconsistency on this path. So this path is called a false path. Okay. That means the longest possible delay or path delay of this, accounting for logical constraints, is 6. Okay, so we knew this. There's a lot of discussion in the CAD community about false paths and circuits and so on and so forth. And then I had a big project that was doing low-level analysis of these. We're looking at the transistors inside these things and how the wires and all of that stuff. And then I had this discussion with a very smart PhD student, circa 1994. For accurate timing analysis, we need to check the logical consistency of circuit paths. We need a SAT solver. What did I know about SAT solvers back then? Not much. I knew that the worst case complexity is exponential. I knew about P not equal to P. What did I say it wrong? P not equal to MP. And I said, okay, go get yourself a SAT solver. So let's finish this project. Student, no existing SAT solver can scale to our problem size. They may possibly handle 50 variables. Our circuits have between 10,000 to 100,000 gates, which means variables. And now he's telling me he's going to go from 50 to 100,000, right? We spent a year arguing, okay? Because my report to NSF has to be about, we found the longest path in a chip, and this guy is doing something else. Well, all is well that ends well, right? He won. So I said, what do you suggest we do instead? He said, we need to develop our own solver. And I said, you got to be kidding, right? Okay. In the end, he said, we can do it. And then after that argument for a year, GRASP was born. Okay. That's how GRASP came about. I can't think of any other way that this could have happened. Maybe another group, another universe could have come up with something like this. But I credit this problem for forcing us to think about how to scale solving these large CNF formulas. By the way, after this, we were flush with cash. Intel gave us a lot of money to find long false paths in their chips. We found tons of them. None of them were the longest. So this killer app, which triggered the development of this, was really not that important after that. Okay, then it became something more important for other applications. Right? That's how it came. Here's his dissertation, the papers and all of that stuff. And then, so this was in 1995, 1996. In 2000, how many of you remember the phase transition phenomenon? Yeah. This was on the evening news. Journalists who had nothing to do with anything were trying to understand what SAT is, right? And the idea was that when you have random 3-set instances, where you so you create uniform formulas, with random 3-set clauses, and you plot the runtime. They were using DPLL back then against the close to variable ratio. They discovered something like physics. They call it the phase transition. Fewer constraints per variable means the problem is easily satisfiable. many more constraints than variables, the problem is easily unsatisfiable. And then at the 4.25, magically, the problems become extremely hard. Well, we became interested in that. We plotted close to variable ratio against what we were doing with graphs and circuits, and we found a scatter plot that wasn't doing that. So we went to the 2000 workshop in the Netherlands to understand what's going on, right? So that's João Paulo, that's me, and I found out this is Armin. So we're all there, you know, a little younger and maybe less wise. And we told them back then that when we did the close to variable ratio on our instances, there was no correlation. And it should be obvious in retrospect. I mean, we're not, you know, doing random formulas. These formulas describe circuits that have some structure. So I started talking about the structure. We need to understand the structure of the formula. What's the structure of the formula? Now, this is a quick summary of now what happened next. So we had GRASP, 1996, Sato, and this is all documented, took what we did in closed learning and incorporated it into their solver. Okay, and then they introduced this head-tail thing for propagation, which then was taken by Chaff, which said we're doing closed learning like GRASP, and we improved on the head-tail thing by doing this two-watch literal thing. Then all of this got included in Minisat. This is 2003, where it also implemented basically Chaff and GRASP, and also took some of the other stuff that we did, which is like incremental solving and also pseudo-Boolean. This is what has been called CDCL. I disagree with that because I think we don't give enough credit to Chaff. You see, GRASP introduced closed learning. By the way, the guy who coined CDCL is by the name of Lawrence Ryan in his dissertation from Simon Fraser. And it doesn't capture everything. You see, GRASP had a very aggressive branching strategy that's called DLIS, dynamic largest something something. At every stage of the search, it finds the literal that will satisfy the most unresolved clauses. It was going for satisfying the most clauses. Chaff said, no. We're going to try and branch on conflicts, you know, promote variables that appear in conflicts. And I like to call that conflict-driven branching. There is a theme over here. The theme is conflict-driven satisfiability is a combination of conflict-driven learning and conflict-driven branching. Everything else is just variations on the theme. So my understanding of what is now, unfortunately, we have to keep calling CDCL, but it's really the combination of these two, is that a conflict-driven SAT solver aggressively attempts to falsify the formula, and when it fails, it produces a satisfying assignment. That's what it is, okay? Now, why does this work? I still don't know. And I dare anybody in this room to tell me how they know that, right? And by the way, we're gonna get to that. The theoretical complexity stuff that has been established only talks about closed learning and assumes that the branching is done in some, you know, way that, you know, will make the proof go through, right? But I really think there is something to this, you know. This is an approach to solving that says, let's aggressively falsify the formula, and then when we fail, we find a solution, okay? There might be other ways to do this, right? But this one seems to work, and I don't think that we have a satisfactory answer for why. This is from 2011. Again, I presented data and nobody paid attention. Okay, this is we took 1,000 instances in different families and so on, and we said, okay, let's understand, you know, the big picture. So this is DPLL. It kind of stopped at about 200. When we added closed learning, but with this aggressive, satisfying branching heuristic, you know, we kind of pushed it up. This is a qualitative improvement, right? It's not like 1% or 5% or, you know, 2 more we solved. And then if we just do branching on conflicts, we do a little bit, we do quite a bit, but not as much as closed learning. You combine the two, and that's what I would call CDSAT. You know, if that's hard to say, CDSAT, just it's conflict-driven solving. Conflict-driven solving is what is going on over here, okay? And the connective tissue between closed learning and conflict-driven branching is this fast propagation that's enabled by two watch litters, because you would learn these long clauses and you need to actually have a quick way of figuring out if the clause becomes uniform. This to me is, what we have today. Everything that happened since then is just, I don't know, noise. That's my harsh. It's noise. Okay. Why do they work so well? Okay. Consider this. This is, thank you. I read the chapter. Not in detail, but I found nice quotes in it, right? So a CDCL solver, this is the reporting result that was done by Darwish and Albert, saying that CDCL solver, unit propagation, closed learning, frequent restarts. Restarts had to be included in proving this, but not branching. Can establish unsatisfiability of a CNF formula in time polynomial in the shortest resolution refutation of that formula. Very nice result. Very nice result. The empirical observation is CDCL solvers routinely establish unsatisfiability of very large CNF formulas that encode human-created artifacts, hardware, software, something that came from somebody's head. Conclusion: these large formulas must have short resolution refutations. But why? Maybe because they have some recognizable structural attributes. Okay, so in the space of all CNF formulas out there, there is a vanishingly small number that come from somebody's head. They don't think CNF, but they're designing something and then gets encoded in CNF, and then it's easy. And the question is, can we actually infer that? Can we know what the intention was in producing these things? So looking back at the phase transition, which we were almost kicked out of the room. That workshop was full of theoreticians who were not satisfied with 4.25 clauses per variable would make it very difficult, but they were kind of having a big, magnifying glass on that and saying it's 4.13752, and it's a waste of time. Okay, a waste of time. So, but one thing stuck to me later is that the closest variable ratio of random tree SAT can be viewed as a structural metric that is predictive of the ease of difficulty of solving the formula using TPLL. So they defined a class of formulas, okay? They're not very interesting from practical perspective, but a class of formulas that could actually correlate runtime with something that has to do with the structure of the formula. It was random. The question here to me is, do large non-random formulas encoding human-created artifacts have structural metrics analogous to the CV ratio, perhaps, of random tree SAT, maybe a bit more sophisticated than that? Are these easy to compute? If we can find them, are they predictive of ease of difficulty of solving the formulas using CDCL? Okay, these are open questions. And I would say that the invention of GRASP was a stroke of luck here, because if we did not have that application, which provided us with very quick solutions, then I would not be at the Simons Institute today. I mean, it's just, it's a fact that they just happened magically to have these short refutations for some reason. Conjecture, because I am not smart enough to, a lot of people in this room who can actually do this much better than I, it was basically a circuit SAT problem. We had gates that have two inputs. And so the CNF clause had 2/3 of the clauses being binary and 1/3 being ternary. That's not enough to kind of make it, go fast. But somehow the constraints were very sparse with a lot of locality. Okay, there is some proof theoretic stuff on circuit SAT, that I think we can talk about that. Maybe that we can explain then why these things that come from circuits, are easy to solve or not, right? There's a colleague who I lost track of. If anybody knows where Carsten Sims is, he would draw these beautiful, not drawing. He has a way to generate these. These are pictures of CNF formulas, right? Actually, they still put them as kind of a little icon in the SAT competition. I have more of them because in 2011 we had the SAT conference at Michigan, and I asked him to please send me these beautiful formulas. We suck when we come to kind of market ourselves, because we're so kind of boring. So when we had these nice pictures, I had them run on a loop, in the were you there 2011? And so students would come in and look at school, because my colleagues in the department have more sexy stuff to put on things. So I this is nice. This is nice. This is not. There is structure, right? There is structure. Okay. Okay. That's a new setup. It's set competition. I stole some slides from a couple of set competitions. I pulled this one from 2021, and it.
We have a characterization of this one.
Do I have a characterization? Yeah. No, this is open. I'm asking for people to start thinking about this. It's a plea, please. Okay, so the goals of the competition are stated over here. They're very clear. Compilation of new challenging benchmarks. Okay. Promotion of set solvers and their development. To which audience? I don't know. Evaluation of current set app solvers. Snapshot. Good. And then this is now from it's still 2021. Okay, we received almost 1,100 submissions, instances. After we eliminated the notice, if solved by miniset within 1 minute, then it's easy. We don't care about it, right? So 952, 352 went into the main track, 600 into the crypto track. Then for the main track, we used 400. You can see all of this, okay? And we did, we selected a bunch of benchmarks, and then the assumption over here is that miniset is our reference, and what we're really comparing is anything that came after that. So every improvement is after that, because if you remove CDCL and CD branching, nothing works. Nothing works. Okay. So where theory and practice parted ways was at that point where, again, quote from the beautiful complexity chapter, it is still mostly an open problem to establish theoretical results about how the commonly used CDCL heuristics contribute or sometimes fail to contribute to the success of CDCL search. So the practitioners are busy just competing with each other to beat the next guy with, I solved one more than you. And the theoreticians are left behind. I mean, you've got nothing to do with this. Absolutely nothing. Because it's impossible. You couldn't even do branching as part of your proof theoretic investigations. So what I'm saying here is that, yeah, I said this just now, okay? If you can do VSIDs even, how can you do the umpteen other options that they have? I spoke at CAV in 2014, and Armin was sitting next to me in a panel, and I was showing on like 5 slides, the various settings for his Ling-a-Ling solver. My problem is I stopped understanding anything that's happening in the field. I don't understand anything. And then here's what happens with the competition, okay? We ran this competition, and that top line here is called the virtual best solver. If any solver solved a problem, then we add it from there. But you look at all of the other solvers, and they're clumped together. They're just, they're statistically insignificant. Yes.
They're all based on same force. They're all based on KISSET or Catechol.
Okay. So the others are what? Okay. Stay tuned. I mean, you might be actually making my point.
Karem, so I think does it work? Okay, doesn't matter. We have also plots with the winners of every year on the same competition set, right? And you clearly see that every year there is progress.
What are these plots?
Oh, I have them on my
Okay,
laptop.
all right, thank you. Okay, stay tuned. I have answers for every question here. I prepared. Okay, so stay tuned. Okay.
That's what you can see.
Yeah. Okay. So my point is, just showing who solved how many is not enough. We need to go deeper than that. Can you explain this one? Okay, this is not only KISSET or something like this, or is it? But there is kind of a gap between these two groups here, and there's no explanation. Yes.
I mean, there is an explanation.
Okay.
So actually, you said last time that there's noise between this and everything that happened. Actually, this explanation is very clear. The difference is whether you use the local search solver or not. And
what's
so
the local search solver?
An SLS, stochastic local search solver.
Okay.
I use the Armin used some version of YALSAT. I actually used walk set because I couldn't use Armin's work. But so that's the clear separation here. That's the three things up there, or the four things up there. That's local search. Everything below, no local search.
Okay.
So that's actually one of the things that isn't noise. There's like maybe two more, I would say, but local search is very significant, and that
Not
shows
in solving unsat problems.
actually
And
even
for
that is-
verification, we pose unsatisfiability instances, so local search is not going to work.
It's a combination of locals.
It's a bit more than that.
What's
So
that?
what it does, it doesn't just do local search. Yeah, it,
Or find bugs.
no. It does actually help even for onset. I'm not going to argue much
Okay,
longer
fine.
here.
We can
It
talk
does-
about that. Okay,
yes, it
if you
flips the-
convince me that we can use local search for the large instances that we create for verification, then I'm willing to say I'm wrong.
So you showed a plot earlier, DPLL versus CDCL.
Yeah.
Those instances today are much easier for many of these solvers. So if you, no, hold on. If you compare GRASP against the latest solvers, there's no competition.
It's
There's
20
no
years
competition.
of development of solvers,
Yeah.
right?
So I mean,
so what is
the
it?
point you're making
Yeah.
is you're just saying that, everything since then is noise, but that doesn't hold up.
No. If you take
It's just
Minisat,
not a
I'm
true
going to show
statement.
you data on Minisat today, which is competing with things that are happening today. I think you guys are all kind of missing
Listen,
the point.
if you can come up with a solver that can do all instances equally well, that would go against the grain of
Okay.
the hardness of the problem itself.
Let me finish. Because I have a positive proposal for you to go forward, because you guys are not doing science. This is a very bold statement, and I'm going to tell you why it's yes.
So I don't understand the evolution of the competitions, but when I was familiar with it 10 years ago, it was the portfolio solvers who were winning the competition because they would choose for each problem which solver they wanted to use. So is portfolio sort of excluded from these competitions?
I don't know. I mean, some of the competitions have portfolio tracks, right? Right. But what my point is that we can do the competition and we can figure out, but we don't understand. Okay, here's my next slide. The annual competition setup, okay? An arbitrary collection of benchmarks. They might have a scheme for doing it, but it's arbitrary. An arbitrary collection of black box solvers. Now, here's the thing. In the last competition, there were 39 solvers. They may be all based on KISSAT or something like that, but I don't know what's inside them. And then they go through this rather continuously changing competition rules, and then Armin wins, okay? How is that science? I don't understand anything. Armin, are you there? Okay, so the competition is about winning. I'm saying research is about understanding and explaining, and that's what has been missing. I sit in this SAT competition or in SAT conferences, and people talk about stuff, and I'm lost. I'm not the smartest guy in the room, but this can't be the way that we do research. So can we do research, please? Can we do research? Okay, research in the natural sciences. I don't know, astronomy, particle physics, whatever. Okay, they have data collection that's extremely expensive. Telescopes, space probes, particle colliders. The community, spends a lot of dollars kind of on instruments that collect data. They collect the data. Then they curate the data. They put it in widely accessible, persistent databases that's available to all the scientists. Then the scientists go and access the data, and they do research in the data. They find patterns in the data. They come up with new things in the data, and the results produced by any researcher can be checked by any other researcher to confirm it. And competition is not about winning. There's nothing to win over here. It's about who is the first to discover something new and interesting in the data. Okay? Yes.
Even though I'm the chair, maybe I can make a comment.
Sure.
So I think sort of the point is a bit off, because we have the conference for science and the competition is not about science, and you're making the claim that the SAT community is is doing science through the competition or claiming to do science, but the competition is not about science really.
I agree, right? But I think it has negatively affected doing the science in the set community. Okay, so let's talk about results research in the unnatural computer science. Okay, and I'm not. This is. I pulled some slides way back from UC Berkeley professor, which I'm going to name, talking about the scientific method and the computer scientific method, right? So I'm going to just focus on SAT. We have very cheap data generation. We control everything. We choose the benchmark, we choose the solvers, we choose what we collect, we choose so we decide what the data is. It's not like we have a, somebody looking into the heavens and figuring out what comes out. We create the data. Then we do not curate the data. Why? Because it's not interesting, not worth the effort. Okay. You may disagree, but hang on. Data analysis, why bother? The data will change next year, and anyway, who cares, about repeatability. And the competition is my solver sold one more than the other one. It's a geeky game show. That's it. Yes.
I would comment. I think it's even worse. I think I see data gets also created based on what current solvers can do.
Yeah.
So data is skewed towards the current technology.
Yes. So we might overlook some ideas that otherwise would have some merit, if we don't do this. So, Mate, say whatever it is.
Okay, I 10 years ago we had a discussion about this, actually, you and me, and I agree to some extent that this is not science, but at the same time the other option is that you do exploratory data analysis and try to understand what is going on, just like in physics, just like in maths.
Okay, but the setup that we have doesn't allow that, so I have a proposal for how to do that.
That sounds great, because I've been working a lot on that, and it's just a lot of work.
By the way,
and no results.
I told Armin, this might be a hostile audience, and this is not just a one. So he's going to be at the SET conference in July, and I said, find, if we can find some time in the conference where we can get a lot of people kind of talking about this. I think we have. It's not me, it's not Armin. It's everybody would have to kind of pitch in to it. Let me show you what the proposal is. I'm saying it's an alternative. That's what I'd like. But since I'm not going to win, a compliment to the competition, right? Let's do at least that. Okay. We need to organize the data generation. Okay. We need to figure out families of formulas. I'm going to show you some examples in a minute that share certain attributes, right? We're going to agree on a single extensible solver that can be the code base for trying different options, to figure out what's going on. In science, you change one thing at a time. You don't do, everything at the same time and then expect that you're going to learn something. You're not going to learn anything from that. And perform experiments that measure some performance metric, whatever it is, when a single configuration is varied across a specific range. And here is kind of, and then curate the data by making it accessible. One of the problems with the competition is every year is separate. It's like a silo of data that we can't really kind of look at and analyze later. So we need to do that. And then this is kind of where I think we can bring some collaboration between theoreticians and practitioners. Form teams of theoreticians and practitioners to carry out deep analysis of the data to tease out statistically significant performance correlations between specific attributes of CNF families and corresponding solver configurations. Okay? Yes.
How do you agree on a single extensible?
Well, we have to discuss that. Okay, because we need to stop saying my solver is better than your solver. We need to talk about what the solver actually does. Okay, so if your solver is the best, we're going to take it as the base and we're going to do that.
But the problem is, Karem, is that right there, there is an issue, because depending on your choice of the so-called single extensible solver, you can get very different conclusions.
We have to figure out how to do that. So in the break, I asked Clark, how many SMT solvers are there? And he mentioned about half a dozen maybe or so, right? How many such solvers do we have so far? Hundreds. That makes no sense. It makes no sense because you cannot do science with 100 different things that you have no idea. Not even the one who created them knows what they're doing. I mean, I will at least admit it to, I don't know why I did that, right? So don't pretend that we're doing science. Please don't pretend that we're doing science. We are competing on, I am gonna beat you. Competition, it's not science. Okay? This is a massive undertaking that requires buy-in from the entire science community, but it holds the promise of invigorating the field, fostering substantive collaboration that enrich both theory and practice. Outside of this community, nobody knows what the heck is happening in set solvers. Nobody outside our community.
What the heck happens in any other system?
No, that's not true.
You know what the heck happens in a circuit?
And what?
In the circuit that you designed, why it performs efficiently? Let's talk about a microprocessor with out-of-order execution.
I think there's a lot more substance to that than what we're doing here. Let's agree to disagree. Okay, I expected a hostile audience, but not from you. I thought I liked you.
And I'm always a friendly guy.
Yeah,
so-
you're
so,
friendly. Yeah, go ahead.
Yeah, so although there are things so the competition has been mostly to be a real kind of more objective measurement of what is the current state of the art. And so I have plots to show that every year there's progress, and we also in the competition reports we argue why we think the progress happened, what are the techniques that contributed, that all the solvers in the next year are adding. But so I do think that such an alternative competition is a good thing.
Okay.
The challenge is only how to get those families, right? Because
Okay.
all these theoretical families
Right.
that
Yeah, I understand.
many practitioners, practice people are not interested in, but we do not know how to get good families.
But we should try and doing that. I mean, that's my point.
But
You know.
I think Moshe has also been arguing for this for a decade.
Yes.
But
The fact that it's difficult to do doesn't mean we shouldn't try and keep
Yeah.
trying. That's it. That's all I'm saying.
Great.
Andy.
So on your point about the a common platform, I'll disagree with it in the following sense. I think the better is actually what's out there now. So actually, there's 3 solvers out there that count for anything. That's KeySat, Catechol, and Miniset, meaning everyone who does work now is building on that code fairly directly. And the fact that all these solvers in the competition have to make their code available afterwards kind of keeps people just grafting in the latest updates. So the code is actually remarkably similar across solvers. And I claim that's a better, even though it's sort of chaotic, anarchic, blah, 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 but trying to get a bunch of people to sit down and say, this shall be our solver and this is the API is going to be, first of all, impossible. And second of all, just cause everything to stagnate. So
Okay. I think
I'd
that
argue for that more
okay.
evolutionary approach that actually exists right now.
3 is okay. 40 is not. That's what I'm saying.
40. There's 3.
Yeah.
Tell me another one that's worth worrying about right now. Crypto mini set. Yes, it's a separate code base. Okay, you got 4. So, but it's not it counts
Okay.
on the fingers of
All right.
2 hands.
Out of all those 4, CryptoMiniSat, not that I want to promote my own solver, but it's the only one that actually has the capability to output the data that you're actually talking about.
Right.
It can output gigabytes of data, then run it through the proof system, connect the proof to the actual behavior of the SAT solver, and actually learn on that. Because I have done the work that you were trying to do with this visualization. I've spent 1.5 to 2 years of my life trying to do it. No, it's a tunnel that ends nowhere. The problem is that visualization it looks really good. It doesn't help. You need exploratory data analysis and you need machine learning, either one of the 2 or both.
I don't want to go to machine learning. Okay.
Well, machine learning is just another. Yeah.
Forget machine learning. We're doing logic here.
Well, okay. You start out talking about conflict-directed solvers, but I like to avoid conflict in meetings.
Well, it's not a conflict. We're just having a conversation here.
There's also this story about the person who says, "Why are you looking for your watch under the light here when you lost it on the other street?"
That's right.
Because there's more light
Yeah.
here, and these are tough problems. But so I just want to, instead of talking about that, I want to talk about my own experience with sorting. I wrote a book about sorting, and let's say I had 25 sorting methods. And then after I finished the book, a year later, I actually was faced with a problem where I had to do sorting. And I was at a loss because I didn't know which one to use. But like you, I think maybe I should have had only 3 sorting methods or something like that. But when I looked at it, there wasn't a single one out of these 25 that I could throw out except bubble sort. And I thought that bubble sort was something, no matter what the application was, I could always do better than bubble sort. And it was interesting because that was one of the first theoretical results was that bubble sort was the optimum method for a particular kind of hardware based on a rotating drum of some kind. All right, so but then later on I found uses for bubble sort, not only because it was a bad example, but also because I could apply it to some physics problem.
Right.
So it might very well be that when we're talking about algorithms, we're going to have to learn how to live with
several,
with a multiplicity.
Right. By the way, I'm not pushing conflict-driven satisfiability. I hope that message is not. I'm not saying that. I'm saying we might be missing something else because we got focused on just doing this. Okay.
May I also make a comment? So. In principle, I am fully on board. More science, more understanding is very good. Maybe in your proposal, because you say to do then a statistical analysis about correlation between families and solvers. But what do we learn about correlation? Isn't causation what we would need to know? What techniques work? Why do they work?
Right.
Correlation.
I'm not done here. So yes, listen. We're running out of time. I just want to show you what we did. Okay, and then you can kick me out, and then I can go home. Okay. So I started talking to Armin about, I don't know, a year and a half ago. We met weekly, and the first thing that we did is he had the SATch solver, which he felt was going to be kind of the way that you can actually change one thing and then see how it affects performance and change the other thing. And then when he showed me the very complex dependency diagram between the options, meaning if I do this, I have to do that, and I said, wait a minute. How many knobs do we have on these things? Okay, we have branching, we have propagation, we have conflict analysis, restarts, deletion, and so on. It couldn't be umpteen different things. Can we just understand? I don't understand them. I don't understand what each is contributing and whether that. So after long conversations, he decided, okay, we're going to have a different prototype called tabula rasa. Okay, the odd couple and the supporting test. Okay, so what we did was we wanted to select benchmarks. So they said, let's select the ones that from the 2022 competition. I said, why? They're different. I cannot get correlations from things that are completely different, right? So can we look? They had a table of 2,400, all the benchmarks that have been collected over the years, and they had some name for a family and so on. So we looked. I wanted to get a large collection of benchmarks from the same family that might have something in common with each other. It was very hard to do that, but we managed. Actually, we had 12 families, but then we discovered that one of them was impossible because it was Armin's family. Nobody solved that. So we ended up with 11 families, 14 instances per family. And we said, okay, so what are we going to check for? Many things we can check. He said his favorite, in processing and pre-processing. I said, fine. So let's do that. Okay. So the students I'm working with, created a database. We need to do a database, guys. Okay. We need to do a database that collects the data across years so that we can go back and say, you were wrong back then when you thought that, because I can do the analysis on it, right? Right now, I don't have that. So we have a benchmark table. We have, what is it? We have the solver tables and the options of the solvers. We have the run table, which is, I get a benchmark and a solver and options for the solver. And I know when I did the benchmark and I saw the result and it stays there. It has a timestamp. We can go back and analyze the data. We don't have to do it once. We can do it many times. We can have a lot of research going over many years, just looking at data and understanding and maybe finding something that we didn't find by just doing the competition. So Armin is a master of naming things. So he came up with these names for these 5 options. Core means no in-processing, no pre-processing, and that's core. Then minisat, vanilla is like minisat. It does only pre-processing, and pre-processing using bounded variable elimination subsumption. Then he had parfait. They're all kind of flavors of ice cream or something that you lick with your tongue. In processing, but no pre-processing. Semifredo does both, in and pre, okay? And then he wanted to go to more sophisticated things, so he came up with stracciatella, which does in processing and pre-processing using additional things like substitution and transitive reduction. Don't ask me what these are because I don't care, okay? But there are 5 things that are independent, supposedly. And now I need to switch to my other presentation here. So these are the options I have to send here now. And so now we're going to do the competition plot. And you can see that they're all bunched up, right? And in fact, that thing that says 79 is minisat. And it's only 2 off from the best one. But this is not honest, you know, this is the honest plot here. Right? Now, what I'm saying is, I don't believe that, you know, CDCL is the best thing since sliced bread. I mean, you know, we need to understand what happened here. You know, why do they, you know, tap off, you know, at that point? I mean, is there something else going on here? But this is like one bit of information about what happened, right? So maybe you're doing this in this competition, but I didn't see it, and maybe I'm just too lazy and I don't look at what you're doing. But here is kind of another way of looking at it, where, you know, all of these are kind of similar. You know, one of them could solve one more than the other, but most of them, half of the benchmarks were not solved in 2 hours. 2 hours on fast, you know, server farms. I'm not defending any of this. So there are lots of questions open here to kind of, you know, see what's going on. Perhaps a more interesting way to look at this is, since the options are really not all that distinguishable from each other, let's see by family how they are. And don't ask me about how the families are. They're named arbitrarily. I mean, the question about, you know, it's hard to do this doesn't mean we shouldn't try. Here you see the distinct differences. There are some families that are hard, okay? Hardware BMC, these are Armin's benchmarks. Strip coloring, you know, look at how many are unsolved. Scheduling school, I don't know what that is. Night chess, okay? Then there are ones that are very easy, okay? What are the easy ones? Mining, I don't know what that is, but it says mining, it's very easy. There is this Lefrieux 2017, we found out this is about range scheduling in France. They're camouflage, so we don't know exactly what the formulas are. These are some of the largest ones. They have, you know, between 1.5 million and 3 million variables in them. They get solved very quickly, right? And there are something in the middle, you know, half, you know, solved, half not solved. I look at this and I'm very curious. What is going on over here? Can we now take a deeper look into what is the actual formulas that we're looking at, and why is, you know, some of them hard to solve and some easy to solve? The other day we heard about the pigeonhole principle, okay? I did FPGA routing years ago, and in FPGA routing, you get pigeonholes, right? You have a channel that can only have like 10 wires in it, and we cannot route more than 10 wires. It's pigeonhole. Now, we know also from complexity theory that you cannot actually encode pigeonhole in CNF and, you know, get any performance. So as a problem solver, of course, I don't want to, you know, encode it that way. I'm going to encode it, you know, pseudo-Boolean constraints or something like that, you know, that has counting in it, right? So from a problem solving point of view, I picked what would be the appropriate encoding. So the problem may be difficult for CNF SAT. That doesn't mean we cannot solve it, right? We can then combine, you know, proof methods in order to get the answer that we want. But the fact that it is actually regular, which is very symmetric, right? We should be able to solve it, right? Instead of trying to prove what's impossible, which I think is important, but I don't know how to do it, I'm trying to find what is possible and make it work, right? And I think now here where the theoreticians come and, you know, you ask about how you do this. You know, you take a look at something like this, right? and you look at the trace, the behavior of the CDCL solver, and maybe these options are not the right ones, for this experiment, but let's look at this. And the theoretician might kind of look at the instance and say to the, the coder, the hacker, right? You say, look, the set solver is doing this. Is there something about this at a higher level that we are missing out? These are circuits that people design. They must have some high-level structure to them. Is there a way we can get that structure in? And then start doing that correlation, Stefan. What I'm saying is not that people have not thought about this. I don't think that we have been doing it enough in order to kind of make the theoreticians and the practitioners come together. As a theoretician, I think they can look at the structure of the instance, right? How the variables and clauses are organized and so forth, and then look at how the solver is doing. Is it learning the right things? Maybe CDCL is not the right thing for it. Maybe something else has to be. This is what goes to Nikolai's idea of if we go to the fastest solver, then we're missing out some ideas that are gonna get ignored. I am not pushing my thing. I'm just trying to say, guys, we have been meeting, we have not been talking. Maybe something like this would start a conversation. Maybe the idea of it's hard. Where is Jacob? He invited me several years ago. When was this? 7 years ago or something like that. And he had these tabling formulas, right? And yes, they might not be interesting, but they can give you trends on these things. I think that could still happen. We could do that. Maybe they can, we can. It's harder for formulas that come from applications because you have to know what the application is and so on and so forth. But I think it's worth doing that, because otherwise we're going to continue finding what is the set solver behind CVC5.
Well, if you heard the talk from yesterday, we now support Catapult. It used to be Minisat.
Okay. And do you have a order of magnitude difference between the performance?
No, because most of the time is spent in the theory solver, but for some problems, it does make a big difference.
Okay. Yeah. So for utilitarian objectives, I have no problem with finding the fastest solver, but to understand why it is solving it, I think we need to do something else. That's my, yes. I gave a version of this that wasn't, like this at 2014, and one of my students from the audience, he said, you sounded angry. I said, okay, I'll try not to sound angry this time, but I'm exasperated because I really want to understand. And if I'm not reading the right literature because it's not showing up in the places that I look at, then that's on me. But I really think we can do better. I think we can. We're ignoring looking at detail like this. I have to do it here. So if you look now at individual families, you can start finding kind of the detail of what the solvers did and what they did not do and so on and so forth. Yes.
Yeah. So although I really like the idea of this approach, I do think that what you're currently showing is not that useful, right? Because
this is an example. It's not.
Yeah, because we really need to have families that you can
exactly
you get.
14 is not enough. It's not statistically significant.
No, but it's not also. You need to kind of generate that you can see. Okay, this every time you have a larger instance, it's maybe 10% or 50% harder. And so to have a clear, because I know these families, they're typically all of the same size. So it's
no, some of them are different sizes. Yeah, some of them are different sizes. Listen, I'm not suggesting that I've solved the problem. What I'm saying is, if you do circuit SAT, right, you can have different circuits of different sizes and different compositions. They must have something in common. They must have the fact that there is some locality in them. There is no right. To just say it can't be done, I didn't do it here because we just started doing this, and I don't intend to spend my life doing this. I'm saying that if we don't think about families, you've classified in the competition families, and some of these families are bogus because they just have the name of the person, and then whoever made the competition rule said only 20 solvers per family, and then you give your students to give them, so you have 40 instead of 20. I mean, I'm not. Winning is fine, but we need to spend a little bit more time.
Yeah, but let's not talk about the rules, which have been quite consistent. we choose at most 14 benchmarks to have a lot of diversity, right? I think that's also very important for a competition to have a lot of diversity.
Well, the thing is, it doesn't explain things. The competition does not explain things. And that's my problem. My problem with the competition is a hodgepodge of things that are completely different and diverse, but when we cannot actually conclude anything other than Carical one or this one. I want something a little deeper than that. I go back to what the people who did the phase transition did, which is they defined a family of benchmarks that they could actually correlate with performance, right? If what I'm hearing from you is that that's not possible to do,
No,
then I will just back up and go home.
I would be happy to see such families, right? But let's the whole community.
So
figure
the whole
out
community
families
needs to come together so that we can advance our understanding. That's all I'm saying. Why are these problems easy to solve? Why are these problems not so easy to solve? We need to do that. That answer has not come through. We don't know. It's all vague. It's all ununderstandable. Okay, I think we need to stop here. So I just want to put my last slide, which is there's a lot more detail, and you can look at these slides. And by the way, I'm not defending any of this. This is just let's do something different. That's all this. Let me see. Okay. Science versus entertainment. I really think we are all capable of doing science, and we should do it, if for no other reason that we suck at entertainment.
All right, thank you, Karem.
Okay, so I just wanted to make a comment since I didn't make my hostile comment yet. Actually, I really appreciate, I know you're trying to be provocative and that's good, it makes people think. And I also agree that understanding is great. I think it is unfair to say that we're not doing science because then you rule out, I sit on the systems floor of a computer science building and everyone there is building systems. And now you're saying you're not doing science because you're building a system. And if you look at the papers about SAT and SMT that are systems papers, they do all these things that you say. They say, here's a set of examples that we didn't understand. We tried this technique. Here's with and without the technique. It's better with the technique. And that now we learned something, right? And all these papers at SAT and SMT, this is the way they write the papers. So maybe you didn't read those, but we've learned a lot about how this works, and that's science. Now, I agree the competition is not about science. That's more about if I'm one of these millions of people who's using a SAT solver, which one do I pick? And the competition is a useful benchmark for helping us see what's the progress and what should I use. And it's entertaining, right?
Right.
So that's a different kind of science, but I don't think it's fair to say that we're not doing science.
Fair enough. The only thing I would add to this is okay, so I need somebody to tell me one major idea that happened after. I mean, all of this is based on Minisat. I heard local search, right? Which is kind of okay. And then we'll have this conversation offline. Would that help with verification? I don't know. What other ideas that have kind of like a statistically significant improvement over Minisat? Like you have Carical. Can you point out exactly what that was? And then we can then say, celebrate this, because this now is a major contribution that works across. Yes.
I mean, glue. Oh,
Glue.
Well, in processing and pre-processing. Okay.
right. Here next.
Here.
So I've tried to do something like this for clique solvers, which are much, much simpler than SAT solvers. They only have 2 or 3 key features. The instances are much simpler and much easier to understand. We can generate large scalable families of doing it. I would suggest that A, this is a much easier place to start looking and to start developing scientific techniques. But also B, that this is really, really hard. And if we can't do it for clique, then why are we aiming to do this for SATs? I mean, to answer a very simple question about why a branching heuristic in clique solvers works, it requires about 1 billion problem instances. The experiments cost me about £20,000 to run. And this is for a solver that is 50 lines of code on a problem which is staggeringly simpler than SAT.
Well, my retort to this is when chat came around, they discovered if we have this adaptive branching strategy on conflicts, that's a major idea, right? And they didn't need billion, things. They just, I'm looking for things like that, that have that statistical. There's a qualitative improvement, that is not so sensitive to many other variations of, problems and so on and so forth. So I don't see that. I'm sorry, but I don't see that. I think.
I haven't read the right papers.
Okay, who else? Who's next? Okay. Yeah.
Yes, so in this room, most of us write papers for SAT conferences and also participate in competitions. And everyone who tries to submit a solver to a competition knows that, or at least I would say it's fair to say that people doing tuning PEP benchmark instances. So this amount of knowledge to tune your solver for the competitions that works maybe with different parameters on different benchmark instances, it's actually very valuable. You don't usually publish it because it's dirty, or maybe it's not very, you can't formulate it nicely, but this competition, then you publish the paper based on something that you learn by tuning your solver for the competition. So I wouldn't say that competition is not science, it actually drives science, but maybe not in somewhat obvious way, right? Because when you tune your solver for the competition, you do a lot of work in understanding why certain parameters work on certain benchmarks.
But tuning the solver for the competition, I mean, I'll go back to Ling, which had like 3,300, I think, parameters. I mean, how can you actually, I mean, I understand wanting to do this. It's a car race, you soup up your engine so that you win. But if you cannot explain what was it that made you win, in a convincing way, not just I solved one more than the other.
But it makes you think, and later maybe you might not be able to formalize it right now.
When is the later? I'm old now. Where is the later?
Next SAT conference.
I don't see it. I'm sorry. Guys, I know that I'm sounding like really. I'm just saying, if we can just change it a little bit so that we can make the data available in the database. Okay, forget everything I said. Let's make the data available so that other people can come in and say we're going to do some deep analysis of the data over time. I think that's valuable. Let's do it. They do it in other science. We're doing experimental science here. Okay. Sorry for the theoreticians, my friends, but most of this is experimental at this point.
Yeah. So you asked about this qualitative difference, and I'm here.
Oh, yeah,
sorry.
Okay. Yeah.
Yes. So qualitative difference. I think you're right in asking that. So my answer, and of course other people's answers will differ. Mine would be LBD, this literal block distance,
Okay.
the glue stuff. The local search integration, I think, is very interesting also from a theoretical perspective. I think it's not a slight integration. It's not like pre-solving or something. It's actual real proper hardcore integration. Okay, very serious and sophisticated integration. Have a look at Armin's work. There's the Cuban Conquer, which is integration of CDCL solvers with Luca solvers. Very serious stuff. It's putting together areas of research and work of different types of SAT solvers. And there is the bounded variable elimination, which basically puts together DPLL solvers and CDCL solvers into one place, because it's effectively a form of DPLL in front of the SAT solver, and actually also in the middle if you're doing it as in processing, which is putting together what used to be called DPLL and CDCL together. I think that's serious and theoretically interesting. And there's vivification, which happens to work very well, and maybe we need to understand a bit better. It's been sort of reinvented a few times. I think that's also the reason why Armin put it into this tabula.
And he's happy that it didn't win.
It's not by chance he did that. I know it's very important. So these are all like except maybe for vivification, which we don't quite understand, the LBD, which you can ask Gilles and Simon. They will both tell you that we have no idea why it works, and we still don't understand. Okay, but fair enough. Those will need to be understood. But these are all like very significant. You put them all into one SAT solver, they'll be very close to KISSA.
I think I'm next. So I agree with everything Mate said, that all these advances that he talked about, you can see that improvement, and the improvement that you see is significant. Having said that, I think the spirit in which, or the place your heart is, I think it's correct. Like the point that you're raising is very valid, meaning that we don't fully understand why some of these techniques work at all. For that matter, we still don't understand why clause learning works. That's a very valid point. But I think there are two separate points here. One is the understanding question, which is, you're right about that. But to say that advances have not been made, I think that's not a fair
I
statement.
didn't say that. I didn't advances were not made.
You
I
said
was saying
everything
that
was
we don't
noise.
understand.
You used the word noise, so it's not
Oh.
clear what you meant. And there's another point. If you take computer science, systems literature, somebody else made this point earlier. I think Clark did. You look at the paper, you look at the advances being made from microprocessors design all the way to operating system, any of that. I mean, often we don't fully understand why these systems work, right? I mean, there are very complicated heuristics interacting in complicated ways that we just cannot understand why or under what circumstances they would perform well, right? The one difference, though, I would say, is that in hardware, they tend to have this very standardized benchmark like LinPack or whatever it is, and they do a huge amount of data collection and data analysis. So I agree with the kind of the points that you're raising, or maybe the way in which you're raising them. I think I would change the tone of that, but the points are valid. Like the two main points, meaning it would be great to have deeper empirical understanding, but I don't think we should put it on the theorists because it's
I think
more
the
on the
theorists need
empirical.
to help us. I really think that the theorists need to come into this picture because
No, probably.
yeah.
Okay,
Yeah.
anyway, it's
Enough.
short on time. Thank you.
Yeah, let me try to also be brief. But so first of all, we have the data from the competitions is all available. So you have there your database. And for example, we had last year, we had the anniversary track. And so we had all the benchmarks of 20 years of competition running all the solvers. So there you have so much data that you can analyze, right?
Can we put it in a database that's accessible to everybody online?
So everything is available online. Everybody here can download it. It has been
It's
online
not
since
downloading
a few weeks after the competitions.
It's not that. It has to be kind of a community kind of available. I mean, what's that?
It's available.
It-
How can you claim that it's not available?
It's not available in a form that makes it easy to actually analyze.
Oh, sure.
Yeah, but
That's not true.
But then you need.
We're computer scientists, we can write programs.
Exactly. Wow. All right.
It's not that
All
big a
right.
deal.
Okay.
It's all there, it's these huge tables, but you can pull all.
What I'm saying is it's not easy for, to make it accessible so that it's easy for everybody to kind of share it.
We don't need GUIs, we're computer scientists.
Not the GUI.
Yeah, and the other point is, so regarding your experiment, right? It's all these clean families, but what you see in practice from all these applications, they are not so clean. And all the techniques like in processing, they really make a big impact on formulas that are not so clean, that come from all kinds of applications, and there's a big impact there. And so that's why you see that these techniques are impactful on the competition, but not in these kind of clean families. But let's, I guess.
We are way beyond the.
Yeah, let's have the final question that we promised, and then we'll have to go for coffee and talk more.
Okay.
So cool that.
So in our group, we have spent last 5 years trying to do something similar, trying to build statistical and causal analysis, mostly led by Mate. I think I like your proposal, but the issue is that if we just want to do science, we'll be probably able to understand why certain things work. But there doesn't seem to be a lot of reward in the community for this understanding, which also seems to be from your presentation, because a lot of times you hinted that if we understand, we are going to get something, new heuristics. And I want to propose that we may not get new heuristic. We may just be able to understand that we have gotten to a good points. So what's your proposal to have enough rewards just for understanding and thinking about a future where we'll be able to understand, but probably it won't lead to any new advance in set solving?
I don't look for a reward. I mean, for me, I don't need any reward. Okay. I just want to make the people that come to these meetings, the computer theorists, the proof theory people, and the people who write the code, to talk to each other. We're not talking to each other. There is nothing going on. So why are we meeting? Let the theorists talk to themselves, and that's what I'm saying. The facade that we're meeting so that we can advance. I mean, I feel sorry for our theory friends because we've created monsters that they cannot analyze. And I'm suggesting a way of doing that. I'm getting pushback. The families are not clean. So I lose. I'm sorry. I mean, it's fine.
Okay, so I think it's time to close. As the main organizer of this series of meetings since 2018, let me respond by saying that I'm happy that we're here meeting and talking about this. So let's continue to do so during the break. Thanks.